Hi. So what we're going to look at here is signal notation. It's just going to be an introductory video, I think, just sort of showing some properties of signal notation when we use it in sequences and sums. And maybe you've seen this letter before. It's a Greek letter sigma. It basically just means to sum. And so if we've got a finite sum that we want to calculate, we can express that as a signal notation rather than having to express it in the long form of the sequence. And we need to be able to convert between the two methods and sort of two ways of expressing these and understand how to convert between them and use both of them. Okay? So let's consider the most basic example of a sequence. 1 plus 1 plus 1 plus 1 plus 1 all the way up to n. Well, whatever the sum is going to essentially be whatever n is. So I can actually just simply express that as a sum from 1 up to n of the function 1, because we're not changing anything to it. If, for example, it was 2 plus 2 plus 2 plus 2, then it would change. So these are just going to be calculated by whatever the value of n is. Okay? And I would be able to prove that for you. And I could say, so let's take the first one, 1 plus 1 plus 1 plus 1 up to n. That's just an arithmetic sequence with the first term as 1 and the common difference being 0. And our standard way of calculating the sum would be to put it into the formula. And therefore proven by our previous method of calculating sums of arithmetic sequences that if we just do 1 plus 1 plus 1 plus 1, it's just going to give us a sum of n. Okay? So if we look at the next example, 1 plus 2 plus 3 plus all the way up to n, hopefully we can see that that is just an arithmetic sequence, and so we need to consider what that's actually going to look like in general. Okay? So you've seen there what I've essentially done. I've then created a sum equation, essentially, with n, and having an arithmetic sequence like that just results in s of n equal to half n plus 1. Now what would that look like in the sum formula? When you think what that function is, well, it's just going to be the function r. Now that actually is given to you in the formula, so if you have a sum from 1 up to n of just a function r, it will allow you to just simply replace that with the formula half n plus 1. And like I said, that formula is given in the exam. Okay? So let's look at a little bit more complicated example. It's not a sum to n, it's got a finite endpoint. I'm just going to get a different colour pen. So what can we do here? Well, let's first of all recognize, hopefully, that it's just an arithmetic sequence. Okay, so then let's look at that again. So there, what I've done is I've calculated what that sum formula is actually going to be. So how would I express that as an actual formula? And then also, how could I calculate, without having to just systematically putting it into a formula, actually calculate what the sum is? So what I could do is, I've calculated the sum formula. Why don't we also calculate the nth term formula? Just going to get another pen. So there, I've expressed that in the formula of just un equals 3n minus 1. And so then, that will actually just give me what the formula is in the sigma notation. Now the problem with this is it's not up to n. If I did that, it's incorrect. If it were to look like that, then it would be correct, but it doesn't look like that. So how could we calculate how many terms that is without simply going 2 plus 5 plus 8 is 3 plus another one plus another one plus another one? Well, we've got the formula un equals 3n plus 1. And that's allowed me to realise that the term 29 is the 10th term. And now I've got a formula for it. Okay? So then how would I calculate what the sum is from 1 up to 10 of 3r minus 1? Well, now I've got it in the sequences formula, what I could actually simply do is, well, I could put it into here first. But since we've got it in the sequence, the sum formula with sigma notation, what I could do is calculate it using that way. What we can actually do is essentially break the brackets and treat it like a function in itself. And then again, if we treated it 3r, we could think of that as just, that's a function r. Every single term is going to be multiplied by 3. And now to continue it, we can use our formula that we've actually calculated that 1 up to n of r is actually just going to be a formula that worked out in example 2. And then from example 1, we know that then the sum from 1 to n, or rather 10 in this case, is just going to be n. But we know that n equals 10. And so what I've done is a very roundabout way of essentially getting us to the sum of that equation, the sum of that sequence is 155. Like I said, this is more just an introduction so we can understand where the sum formulas actually really come from. Okay, the signal notation. So we'll do this one last one. I've got a series, has an nth term un equal to 3n minus 5. Okay? Let's express that sum to n terms as a function of n. Okay? So basically what I want to do is get that as a sequence. Okay? So what I can just do is that it's just going to be so now hopefully what you can start to see is this allows us to, from a geometric sequence, start to get better expressions for sums, as opposed to maybe what we've done in the first one where we started from the sequence. Sequences can be a lot more complicated, but we've already got the algebraic sequence. What if we wanted to calculate the sum from it? Okay, so now using what we know, we can just start to break that down and get what the formula is actually going to become. Now I've broken it down just into individual components that I understand and know. And that has allowed us to calculate what the sum would be given a term of n. So I've given you, started from an algebraic version of the nth term, and then I've been able to calculate what the sequence is, the sum formula is from that, without having to work out individual digits of the sequence and then do it a very long-winded way. So maybe example 3 seems a long-winded way of doing it, but example 4 means I've gone straight from the algebraic term of n straight to s of n. Which then means if you were then to ask to calculate, say, s of 15, you could just put it straight to the formula. Okay? So hopefully that has introduced signal notation for you. I'm going to do another video after this, which is maybe more calculations stuff and showing 2 more properties of certain formulas, particularly similar ones to that. Okay? So, see you in the next video.